In this video, we're going to look at how we can use electrochemistry to define the Gibbs energy of formation for individual ions in a solution. So we have our electrochemical cell here, which we have set up like so. So we have tin being oxidized to tin 2+ ions in aqueous solution, and we have hydrogen ions being reduced to H2 gas with an inert platinum electrode. Okay, so if we take those two half cells, turn them into a net ionic reaction, we would get solid tin plus 2 aqueous hydrogen ions yields our products of aqueous tin 2+ ions plus H2 gas. Okay, so if we wanted to calculate what the standard Gibbs energy of this reaction would be, we would use the Nernst equation. We'd say delta R G naught is equal to minus number of electrons transferred times Faraday's constant times the E naught of the cell. Okay, so we know the standard reduction potentials of each of these parts of our cell. So we know E naught for our oxidation here is the oxidation of tin to form tin 2+. Its standard reduction potential is minus 0.136 volts. So its oxidation potential is going to be plus 0.136 volts. Oxidation is just the opposite of reduction in terms of what the value of the EMF is. And for the reduction that's taking place here, it's the reduction of H+ ions to H2 in the standard hydrogen electrode under standard conditions here. So if your acid was 1 molar or a unit activity, then your standard reduction potential here for the standard hydrogen electrode, as the name suggests, is 0 volts. Okay, so that means that our E naught of the cell is just equal to the reduction plus the oxidation is equal to plus 0.136 volts. That's our E naught for our cell. So we can calculate the Gibbs energy of reaction for the cell, the standard Gibbs energy of reaction, minus number of moles of electrons. There are 2 moles of electrons transferred in this reaction. 2 leave the tin and 2 go to the hydrogen ions. Times Faraday's constant, 96,485 coulombs per mole, charge of the electron times Avogadro's number, times our EMF, standard EMF of the cell, which is positive 0.136 volts. So our standard Gibbs energy is going to be equal to, if you convert that Gibbs energy of reaction into kilojoules per mole, what you'll get is minus 26.2 kilojoules per mole. Just take the value you get here, divide it by 1,000, because 1 volt is equal to 1 joule per coulomb. Okay, so that's our Gibbs energy of the reaction there. But we know we can calculate this value in terms of standard Gibbs energy of formation as well. So we can say delta G, let me go to the other side of the page here. We can say the standard delta G of reaction here for our total reaction is going to equal the, well, let's just go through and do it. So it's going to equal standard Gibbs energy of formation of H2 gas times only 1 mole of that, plus our other product is 1 mole of tin ions, aqueous tin ions, minus for our reactants, we have 2 times the standard Gibbs energy of formation of aqueous H+ ions, minus stoichiometric coefficient of 1 for standard Gibbs energy of formation for solid tin. But there are several items in here which are in their standard states. So solid tin is the standard state of tin, so its Gibbs energy of formation is 0, because that would be no net reaction. Solid tin is the standard state of tin. Similarly, hydrogen gas is the standard state of hydrogen, so its Gibbs energy of formation is 0. So what that leaves is that our Gibbs energy of formation here, our Gibbs energy of reaction, this minus 26.2 kilojoules per mole, is equal to the standard Gibbs energy of formation of aqueous tin ions, tin 2 plus, minus 2 times the standard Gibbs energy of formation for aqueous hydrogen ions. So we now have a dilemma, because for any pair of ions you would have such a case like this where you would have some Gibbs energy of reaction, but you wouldn't be able to narrow it down to more than 2 ions at a time. So without picking some ion as kind of a standard ion which has no Gibbs energy of formation, we're really left without any further options for what we can do to simplify this result. So what we're going to do as a result is we're going to define the Gibbs energy of formation for hydrogen ions to be 0. So this is also going to be defined to be 0, just as elements in their standard state are defined to have 0 Gibbs energy of formation, or standard Gibbs energy of formation. So what that means is, since this hydrogen ion is 0, we can measure what the Gibbs energy of reaction is for any kind of standard aqueous ion like this. And we can build a table of the standard Gibbs energy of formation for a lot of metal ions, which we could then use to calculate the values for the corresponding anions. So in fact, electrochemistry, with the addition of this definition here, gives us the ability to define standard Gibbs energy of formation for a lot of aqueous ions, which can help us in defining what the Gibbs energy of reaction is for all kinds of aqueous reactions.